Okay, today we're going to take a look at 4 more examples of related rate problems. In this example, we have a coffee pot. Now, the picture over here doesn't really look like a coffee pot to me. I don't know, maybe if you put a handle on it or something. But nah, it still doesn't look like a coffee pot. But it does say that it's in the shape of a cylinder. The radius is a constant 7 inches. So the radius is always 7 inches. It says let H be the depth of the coffee pot. So they're showing you right here that's how much coffee's in there. It says it's measured in inches. And it does say that H is a function of time. So the more time that passes, the more coffee is coming out of it. Time is measured in seconds. It says the volume V of coffee in the pot is changing at this rate. So the rate that V changes is going to be V prime. So we can write that somewhere. V prime equals, because the volume is decreasing, we're going to make sure it's negative, 3 pi h. That's going to be important later. Of course, it's volume, so it has to be cubic inches, and then the time is seconds, so it says per second. Now, most AP test questions will give you the volume. The only time they don't is maybe if it's a square or a circle or something super easy. But otherwise, they usually give you the volume formula because they want to test your calculus, not your geometry. Now, in this question, it says find the value of dH dt in terms of h. So your final answer will be a function of h. Now, this volume formula has an h in it, so when we do the derivative, we will get an h prime, and that's good because that's our final answer. However, we do have one constant amount here. The radius is 7. So we're going to want to plug in the 7 before we do the derivative. And that way we won't have to do the product rule. Instead of having an r and an h, we'll just have an h because the r will be replaced with a 7. Okay, let's do that. Let's plug in the 7 for the r. You're going to have 7 squared, so that'll be 49. So our volume is going to be 49 pi times h. And now we can do the derivative. Now, when we do the derivative, this is just a constant, so we're really just doing the derivative of h. The derivative of h is a 1, except we're doing d dt, and that's not a t, so we have to do the chain rule, and that's where we're getting the h prime from. If you remember from earlier, our v prime is negative 3 pi h, so we can plug that in for our v prime, and then we can solve for dH dt, because dH dt is our final answer. Okay, in order to solve for dH dt, I'm going to have to divide both sides by 49 pi. On the right side of the equation, all of this stuff will cancel, and you're just going to have dH dt. On the left side of the equation, the pi's will cancel, and you're just going to be left with negative 3h over 49. Now we do want to include units. H is a length, so it's not going to be like an area where you might have square feet or square inches. It's just a length, so it's just going to be inches. And the time is going to be seconds, because those are the only units used in this problem. So it's just going to be inches per second. Okay, and that's our final answer. H prime equals negative 3h over 49 inches per second. So that's the rate that h is changing as a function of h. Okay, this example is similar to the last one, except the r is going to be changing and the h is going to be changing as time changes. So there's no constant that we can plug in, and that's going to result in us having to do a product rule. Here it says oil is leaking from a pipeline on the surface of a lake and forms an oil slick whose volume increases at a constant rate of 1,000 cubic centimeters per minute. So the volume is increasing at that rate. So that's the V prime. So we're going to write that right here. V prime is equal to 1,000 cubic centimeters per minute. And we want V prime to be positive 1,000 because the volume is increasing by that amount. The oil slick takes the form of a right circular cylinder with both its radius and height changing with time. So because the R and the H are both changing with time, we cannot plug any constants in for the R or the H. So like I said, we're going to end up with a product rule. At the instant when the radius is 53, so the radius is changing, but we're going to stop at the moment when the radius is 53 centimeters. and also when the height is 0.2 centimeters. We're going to stop at that moment. And at that moment, the radius is increasing at a rate of 1.5 centimeters per minute. So r is the radius, but r prime would be the rate that the radius is increasing. So r prime is going to be the 1.5 centimeters per minute. We'll write that over here. Remember, r prime can be written also as dr dt, so you can write it either way. And the question is that at this instant, what is the rate of change of h? So h is the height. The rate of change of the height would be h prime. So our final answer is going to be h prime. Now this equation does have an h, so if I do this kind of derivative, I will get an h prime because that's the wrong letter. Let's go ahead and do the derivative. The derivative of v is going to be 1, but then we're going to have to do dv dt because it's the wrong letter. I'm going to make my first thing pi r squared, and my second thing the h, and I'll do the product rule. So it's going to be the first times the derivative of the second, and that'll be dh dt, plus the second, that'll just be h, times the derivative of the first. The derivative of pi r squared is going to be 2 pi r, and then r prime, but I'll write that as dr dt. Remember, our final answer is going to be dh dt. Let me put a box around that. That's our final answer, dh dt. And I can plug in all the other values. I know that dv dt is 1,000 cubic centimeters per minute. I know that r is 53 centimeters. The height is 0.2 centimeters. The radius is 53 centimeters. And r prime is 1.5 centimeters. I can subtract all this stuff from both sides. And then I can divide by pi times 53 squared on both sides. And that's my final answer. We do want to include the units. Remember, h is just the length. The only length that we've used in this problem was centimeters. And the time is going to be minutes. And that's our final answer. We can plug it into the graphing calculator to get a decimal approximation. If this was a real free response question on the AP test, I would just stop here and leave it like that. Remember, you do not need to simplify simple arithmetic. But let's plug it in the graphing calculator and see what the decimal would be. Okay, as a decimal, we're getting 0.101997. Remember, the units are centimeters per minute. You can leave it like this on the AP test. They will only look at the first 3 digits. Or if you do want to round it to 3 decimals, I would just truncate it. So that would get rid of the 997. Of course, on the AP test, they would accept 0.102 because the next number was 9, and the 9 would round the 1 up to a 2. But I always say just truncate it. You don't want to spend time thinking about whether or not you got to round up or round down. It doesn't take a lot of time, but every little second counts. So why waste the time doing it? And who knows, you might even make a mistake. Okay, this is the easiest one out of all of them. The only difficult thing about this one is they give you a table, so you're supposed to get r prime from the table. So when t is 2, the r prime is 4, and we get that from a table. Other than that, this is an extremely easy problem. We have a sphere. They give you the volume of the sphere. Okay, it says the volume of a spherical balloon expands as the air inside the balloon is heated. So we know the volume is increasing, so V prime should be positive. After reading it, we're going to see that our answer is V prime. We got to make sure that that's positive. The radius of the balloon in feet is modeled by a twice differentiable function r of time, where t is measured in minutes. The table above gives selected values of the rate of change, r prime, of the radius of the balloon over the time interval from t equals 0 to t equals 12. The radius of the balloon is 25 feet when t equals 2. So the radius is going to be constantly increasing, but we're going to stop at the moment when t is 2, and at that moment the radius is 25 feet. Let me write that down. So when t is 2, the radius is 25 feet. Again, it does give you the volume of the sphere, so we're going to write that down right here. And it asks us to find the rate of change of the volume. So V is the volume. The rate of change of the volume would be V prime. So we need to find V prime. That's our answer. And remember, the volume of the balloon is increasing, so V prime should be positive. We want to remember that. So we want to find v prime when t is 2. Since we have v, we can find v prime just by doing the derivative. But we're going to do this kind of a derivative where t is the variable. Notice none of these letters are t. So for the first one, when I do the derivative of v, I'm going to get 1, but it's the wrong letter. So then I'm going to have to do v prime. The 4 pi over 3 is a constant. So I'm just doing the derivative of r to the third, and that will be 3r squared. But r is the wrong letter, so I got to do the chain rule. I got to do the derivative of r, and that's going to give me dr dt. Now the whole point of this problem was to find dr dt from the chart. Remember, it's when t is 2. So when t is 2, you can see that r prime is 4. So we're going to plug in a 4 for r prime. The units are feet per minute. The radius is 25, so we can plug that in. You might notice that the 3 on top will cancel with the 3 on the bottom, and we're just left with 4 pi. Okay, if you multiply this out, you get 10,000 pi. If you want to write it as a decimal, you would get this. And remember, we want to truncate it, so we're going to cut it off right here. So the decimal at the end will be 926, or you could also put 927 if you want to round it up. Don't forget the units. On this question, if you don't put the units, you will lose points because it does say to indicate units of measure. So because it's volume, the units are going to be cubic feet per minute. If it was an area like dA dt, it would be square feet per minute. And if it was something with just a length like dr dt, then that would just be feet per minute. So that's our final answer. Okay, here's our last example. This example is going to be a similar triangle example. We've done those before. Here it says the top half of a cone is full of water. What do you mean the top half of a cone? Well, a true cone has a top and it has a bottom. So when you buy your ice cream cone and they only give you part of it, you're getting ripped off. You should say, hey, where's the other half of my cone? Of course, if they gave you both halves of the ice cream cone, all the ice cream in the bottom would fall out. But anyways, the top half of a cone is full of water that is draining at a constant rate of 0.2 cubic feet per minute. Now, if the water is draining out of the bottom, that means the volume inside the top of the cone is decreasing. So if the volume is decreasing, then the derivative has to be negative. Don't forget that. That's probably the most important part of the problem. So our v prime is going to equal negative 0.2. The negative is the most important part of that. That's usually the common mistake. That's where people usually mess up. Now the cone is 6 feet tall and the radius of the base is 3 feet. It wants to know how fast is the height changing at the moment that the radius is equal to 1. So the radius is changing, but we're going to stop at the moment that the radius is equal to 1. Now you can see we do have similar triangles here. The reason why they're similar is that they both have a right angle right here, and they both share this angle down at the bottom. So if 2 of the angles are congruent, then all 3 have to be congruent. So we have similar triangles. The top is going to be 3. This is going to be r. This is going to be h. And this entire distance here is going to be 6. So we can create a big triangle and a little triangle, and then we can come up with our similar triangles ratio. So I can say r over h is equal to 3 over 6. And this can be solved for either r or h. It does not matter. If I solve it for r, I get that r equals 1/2 h. Or if I solve it for h, I get that h is equal to 2r. Now remember what your final answer is going to be. It wants to know how fast the height h is changing, so it wants h prime. So our answer is going to be h prime. So we're going to have to keep the h, but we're going to have to get rid of the r. We don't know r prime, so it's not going to do us any good to leave the r there. So we're going to trade the r for 1/2 h. We'll plug that in. The r is 1/2 h. And because both things are squared, we actually have an h squared and a 1/2 squared. So h squared times h is going to be h to the third. And then we have all these constants in front. I'm just going to leave them alone for now. Now we're going to take this volume formula and we'll do the derivative. We are looking for h prime, but when we do the derivative of h to the third, we will get our h prime. So let's do the derivative. The derivative of v is just going to be v prime, or you can say dv dt. The derivative of h to the third is going to be 3h squared, but then I need to do the chain rule because I'm doing d dt, and none of these things are t. So that'll give me h prime, or another way of saying it is dh dt. That's good because that's going to be my final answer. Okay, I want you to notice that you can cancel this 3 with this 3. We want to plug in for h, but we weren't given h, we were given r. But that's okay because we have a formula for h in terms of r. If we plug in r equals 1, we get h equals 2 times 1. So h would equal 2. So we can plug in a 2 for the h. Okay, now I think you can see why I left the 1/2 and the 1/2. It's because it's going to cancel with the 2 squared. So all this stuff cancels here, and I'm just left with pi times dh dt. We know v prime, that's negative 0.2. And because we're solving for dh dt, we can just divide by pi and we'll be done. Our final answer is that h prime is equal to negative 0.2 over pi. We can type it in a graphing calculator if we want a decimal answer. Okay, the calculator is giving me negative 0.6366. Remember, we're going to truncate it, so we're going to cut off that last 6. That's gone. Of course, if you wanted to round it up, you could. That would become a 7. Let's not forget the units. This is h prime. So h is kind of like a length. It's just going to be feet. And the time is going to be minutes, so it's per minute. So our final answer is that h prime is equal to negative 0.636 feet per minute.